Good morning. I'm going to present cross-validation on gas measurement system between GC and USM. Before I start with the cross-validation between GC and USM, I'm going to talk about the existing USM diagnostic monitoring methods. For ultrasonic meter, some of the existing diagnostic method that we have, the first one is speed of sound check. We check difference from mean. We also then check difference between the average speed of sound and the AGA-10 calculated speed of sound. The other thing that we check is the velocity profile check. We can check the profile factor and the symmetry ratio, turbulence and swirl. And then we also able to check signal to noise ratio and gain. We check this against a footprint. So we have a look at what kind of footprint we have from the calibration results in comparison to the actual result of the gain and signal to noise ratio. We then compare this against the high and low limits. The issue with the current existing monitoring method is that the current footprint comparison method must be made on the similar pressure. So if we have a completely different pressure from what we use during the footprinting, then we will not get a representative result. In terms of footprinting, there are multiple different ways of doing it. The first way is by looking at the standard deviation and the mean of the initial data that we have. In this example here, we look at the standard deviation and mean of the turbulence. So in this particular case, we can see that the turbulence have mean of 3.55% with standard deviation of 0.5%, which is a very good result. So during the actual operation, we compare this result against the actual operation result. The other way of getting a footprint is that by building a parametric model using independent variables. We can improve footprints using this parametric modeling. The more accurate model that we have, the better it will be, because we can then reduce the alarm limit, and then therefore we can have a better improved detection of issues in the USM. So this is the example of a parametric model. In this particular case, this is the data that is simulated, so it's not really representative of the actual data, but it is created to show the power of the multivariate footprinting. So in this particular case, we show that there is a velocity of gas, and then there is also pressure, and then we want to model gain or automatic gain control using these two parameters. So as you can see here, using this parameter, the simulated data, we got an AGC that sits like this. So we got a steady pressure here, and then velocity goes up, and you can see that the gain is slightly going up, and then as the pressure went up higher, then we have a jump in the AGC, and then we simulate that the pressure is steady again with a velocity that's increasing. We can have quite a linear results over there. Okay, when we model this data, this result, if we were to use the model only based on the velocity of gas, we got a result that looks like this on the pink line. And this is actually using a second order polynomial. If we were to use the third order polynomial, the result will look like this. Okay, so the result, the estimation of the result is following roughly where it should be, but it's not exactly the same. So this is the result of the AGC model using a single parameter, single parameter footprint, which is the velocity, and you can see that it doesn't really follow the line in this chart. Here we want to introduce a new patent pending method. In our new patent pending method, we use 2 or more independent variables to create a model to footprint a diagnostic indicator. In this case, our diagnostic indicator is AGC, and we are using 2 independent variables, which is pressure and velocity, to model our footprint AGC. If we see the trend that we show here between AGC and velocity, you can then see that the model tracks the actual data almost perfectly. So this is the model between AGC and velocity in the trend, but the actual variables that's used to model the AGC is actually both velocity and pressure. We only show the trend between AGC and velocity in this case. If we then look at the AGC in terms of time, we can actually see that the data of the model follows almost perfectly to where we are expecting the data to be. This way we can actually then use our footprint data to verify that everything is okay with our USM in terms of AGC. Now, in comparison to the data that you see here, which is only using the model based on the velocity, we can see that the model based on the velocity and pressure is significantly better than the model that only rely on single parameters. So here's a real life example, and as you can see here, we are modeling the AGC using pressure and velocity again. And in this particular case, the data that we show is the AGC against the pressure, and this data is from prior 5th of April. What we then do, we then compare the measured AGC value against the footprinted data. So this, what you can see here, is the data between 16th of May to 1st of June. You can actually see the comparison between the footprint data, which is in this case, the top one is gray is the footprint data, and red is the actual data. On the bottom bit, the blue one is the is the actual data, and the yellow one is the footprinted data. So as you can see here, using the multivariate model, footprint of AGC accurately follows real life data. Now, if we compare it against the footprint that is done based on velocity only, you can then see the yellow line here is the footprint that is based on velocity only. Although in average it looks similar, but it doesn't really show a very representative result of the actual AGC. So based on this, we can conclude that single variable footprint misses the true cause and effect relationship, and it's not as good as the multivariate footprinting. That's the diagnostic for the USM. Now we'll have a look at the existing GC diagnostic monitoring method. On here, I'm not going to discuss in detail every single one of them, but I'm just going to show you what's available right now to confirm that our GC is in a good state. The first one is the ISO 10723 method, and this is normally done either once a year or once every periodic performance, every periodic time. And the idea is to confirm the performance of the GC is still valid within a certain uncertainty limit, within a certain linear area of the GC, of the measurement. The other tool that we have is GCAS. It's a condition-based monitoring tool for gas chromatography, and As a summary, GCAS optimize response factor trend and correlation method, optimize the GC based on the response factor trend and correlation method. We then footprint the data of the GC from that particular healthy state, and from there onward, GCAS then monitor the life uncertainty of the GC based on the calibration reproducibility. GCAS also perform comparison between single point versus multi-level calibration data. So the multi-level calibration data comes from the ISO 10723, so that can be monitored and compared against the single point calibration results within GCAS, and therefore we can actually then see the impact of the nonlinearity of the GC in real time. We can then also perform cross-validation against second GC that measure the same gas. So in a lot of places, there is two GCs measuring the same gas, acting as duty standby, and we can perform cross-validation between them to make sure that both GC is working correctly. And GCAS can also do lifetime calculation. There are some other checks that we can do. People tend to do routine repeatability tests, although using a condition-based monitoring tool like GCAS, that can be replaced by uncertainty calculation. There are daily checks of calibration gas pressure, carrier gas pressure, the situation surrounding the GC that people or technicians check on site, and then people also do spot sample tests, which is basically taking the gas composition from the line and then send it to lab to be compared against the GC at a later date. This is basically determines the health of the GC. Most of it determines the health of the GC. However, it does not confirm the condition of the sample letdown system, although the spot sample test confirms that, although it's not a live data analysis, but the periodic spot sample test can be a good way if we can get a representative sample to compare the GC result against a calibration lab result or a laboratory lab result. Right, so now we're going to talk about the cross-validation between the GC and the USM. When we have a ultrasonic meter system, there is a device interconnection between all the devices within the metering skid. We actually have the USM, we got pressure transmitter, then we got temperature transmitter, and then we got gas composition that comes from the GC that is fed through pressure letdown system. So the way it works, USM will produce or provide gross volume flow rate. Now the health of the USM determined from the calibration and also the diagnostic parameters of the USM. So therefore we have a way to analyze that the USM is healthy. Some of the ways has been explained as well at the beginning of this presentation. Following the gross volume flow rate, we then calculate the standard volume flow rate, and the standard volume flow rate is calculated by multiplying gross volume flow rate to the line density and then divide by base density. So the determination of the line density and base density is dependent on the pressure, temperature, and gas composition. So the health of this parameter is basically dependent on pressure transmitter, temperature transmitter, and the GC health. And then following that, we can then calculate the energy flow rate, and the energy flow rate is basically the standard volume flow rate multiplied by the calorific value. And the health of this energy flow rate is dependent on the GC health. So the question is, we have all this information in hand. Can we then use these instruments to cross-check each other? So there is two parameters that we can check in relation to gas chromatography as well as the ultrasonic meter. So we can cross-check the gas density, and then we can cross-check the speed of sound. For the gas density, there's what we call kappa method. This was presented by Christian Hagenfeld and Dennis Van Putten in Global Measurement Workshop last year, 2024, in Aberdeen. Basically, it's introduced that we can actually calculate gas density using the measured speed of sound isentropic exponent that is calculated by Agae in combination with pressure to calculate the density. We can then also calculate the Agae as a calculation for the density. So the Agae uses gas composition, pressure, and temperature to calculate compressibility and density. So therefore, we got two methods that uses different parameters to calculate the density, and therefore we can use these two methods to cross-check between the two parameters. Ideally, these two parameters are the same. The other thing that we can use is the speed of sound. Ultrasonic meter measures speed of sound directly, while AGA-10 method calculates the speed of sound from the gas composition. To perform this test, we're using a tool called SMA, which is short for Smart Meter Analytics. This is a new software that we have, and this software can actually calculate pretty much everything as long as we know the math. So in this particular case, we introduce input of gas composition with a variation of the typical calibration gas. Variation means the uncertainty of the calibration gas. And then we introduce pressure with 60 bar A with a variation of plus minus 0.25% of a span, which is assumed at 100 bar. Then we also input the temperature, 40 degrees Celsius, plus minus 0.5 degrees Celsius, which is the typical tolerance used for the temperature. And then we also introduce gross volume flow rate, of which 5,300 meter cube per hour. And then we assume that the uncertainty of it, or the variation of it, is plus minus 0.56%. So what we then do, we also put three other meters in there: meter 1 GC faulty, meter 1 pressure faulty, and meter 1 temperature faulty. So on the meter 1 GC faulty, every other parameters remains the same, but we introduce error on the hexane. On the pressure faulty, all parameters the same, but we introduce the pressure fault, pressure bias, and then on temperature faulty, we introduce temperature bias in there. From there, we can then calculate all the outputs. So the outputs are all calculated by SMA using the DLL. So we create DLL functions of AGA8, DLL function of standard volume flow rate, life uncertainty, kappa density, and we also did the footprinting on here. Everything is done on the SMA. So we can then, therefore, following that, compare all these results within this tool. To explain the test setup, the following is the result based on the gas composition, pressure, and temperature that we have introduced to the system. So we got a velocity of sound or speed of sound that's coming from meter 1 measure SOS, and then we also compare it against the meter 1 AGA-10 SOS. So if you see this particular trend here, we are basically seeing two data here. The first data is from measure SOS, the second data is AGA-10 SOS. As this is a simulation data, we make sure that this is the ideal situation. So the measure SOS, we basically enter that manually, which is the same as the AGA-10 SOS. So therefore, we got a perfect alignment between them two as the initial basis for our test. From there, we then calculate the density. We calculate the density using AGA8, and then we also calculate the density using kappa method. And based on these two calculations, you can also see that the two data are in perfect alignment. It actually gives the same exact result between calculated by AGA8 density and calculated using the kappa density. So now I'm going to talk about the impact. So we've introduced the pressure fault. What we did, we actually increased the pressure by 1%. So in this particular trend, you can see this is the expected pressure, which is the blue trend. And then the red trend here is we're introducing the error on the pressure by 1%. What's really interesting here, when we calculate the uncertainty, we look into the uncertainty of the pressure transmitter, the actual pressure transmitter uncertainty actually decreased. So initial uncertainty was 0.416%, and then it decreased to 0.412%. And the decrease of this is because the pressure transmitter uncertainty is 0.25% of a span. And then when we look at the percentage of the actual value, it actually increased the uncertainty because the pressure reading is increased. Now, the uncertainty value does not describe the bias at all. It just purely look at the value of the pressure that we have at the moment. And then if we look at the standard volume uncertainty, also decrease because the pressure uncertainty decreases. That means like overall standard volume uncertainty also decrease. But when we look at the density calculation, we can see over here is that the density increase. If we focus our attention to this box here, we can see that the AGA8 density and the kappa density actually have a very, very similar result. So that line, the yellow line that you see here, is actually yellow line and red line. Red line is invisible because it just sits behind the yellow line, and the value is very, very similar. And if you see, the correct density is the blue line, and you can see that as the pressure goes up by 1%, the density also goes up by about 1%. What's really interesting as well, the speed of sound, you hardly see any difference on the speed of sound with that change. So with the pressure change, the speed of sound actually deviate from what it should be by 0.003%. However, the impact on the standard volume flow rate is 1%. Now, the conclusion for this is because we are monitoring in the real life data, we are monitoring the difference between the AGA density and the kappa density, this particular bit, we don't really tend to see any difference between AGA density and the kappa density, and therefore the pressure transmitter or pressure information is not very useful in terms of cross-diagnostic between USM and GC. So we cannot use pressure measurement for it or to identify issue with the pressure transmitter using this method. Now, the impact of temperature fault, I'm doing also, I introduce 1% fault on the temperature. This is in Kelvin term. And 1% fault in the temperature actually causing the uncertainty of the temperature to go down as well. So it's similar to the pressure, the uncertainty went down, although we've introduced bias on the temperature transmitter. The impact on the density is quite interesting because if you see in that particular box, the correct density comparisons against the kappa density, there's only 0.16% discrepancy. So the kappa density went down by 0.16%. The AGA density, however, went down by 1.4%. So if you see the speed of sound as well, in terms of that particular bit, the discrepancy on the speed of sound is 0.6%. So you can see the discrepancy on the speed of sound is about half of the discrepancy between the AGA density and the correct density. So also because of that, the standard volume flow rate, we also see that there is a discrepancy in the standard volume flow rate. Using the kappa method, there's only discrepancy of 0.16%, but if you were to use the AGA-8 flow rate method, the discrepancy is 1.4%, which is quite a significant difference in that. However, what's really interesting here is that we got a potential for cross-diagnostic between USM and GC, and that is by comparing the kappa density result against the AGA density result. If there is a deviation that is more than expected on the kappa density, between kappa density and AGA density, this could mean a temperature fault. Okay, now the third case is what is the impact from the composition fault? So what we have here, we got a hexane component that normally sits at 0.12%. So the simulation that I did, I basically made the hexane component to read 0.06% instead of 0.12%. So the impact on it is that we got a reduction in the density. So if we compare the agate density against the correct density, we got a reduction of 0.31%. But if we compare it, the correct density against the kappa density, we got an increase of 0.06%. But if you see the deviation between the kappa density here and the agate density, we actually got a discrepancy of about 0.37%. And then if we see the speed of sound, we can see that the speed of sound discrepancy is about 0.19% there. And again, the discrepancy and speed of sound is about half in comparison to the discrepancy between the kappa density against the agate density. But then if we derive the standard volume flow rate based on the agate density versus the correct standard volume flow rate, is actually not too much of a difference in there. We got 0.06%. However, it will actually introduce some error in the CV because of the loss of the hexane in there. But the main idea is that we can actually utilize the kappa method comparison against the AGA-8 density method as our cross-diagnostic feature, because it can actually give us a sign that there is some issue on the GC. So here the example for the standard volume flow rate derived from the kappa density, and it's got like 0.31% error if we were to use a kappa density instead of the AGA-8 density for the error in the gas composition. Now, here's a real life data that we have done. We've actually performing a trial for the ultrasonic meter CPM, which is based also on the SMA. Using this, we can then see a comparison between kappa density and AGA-8 density. It has a discrepancy of 0.033%, which is very, very good. And in comparison to the speed of sound discrepancy between AGA-10 and the measured speed of sound, we got a discrepancy of only 0.0165%. Now consider this, there's a previous paper talking about discrepancy of 0.2% considered to be acceptable for the comparison between AGA-10 and the measured speed of sound. This is actually about 10 times better than acceptable tolerance of 0.2% on the speed of sound. So the idea here is that we can understand the actual capability of our USM, and therefore we can have a lot smaller tolerance to catch issue early, and therefore we can handle the issue with the USM or the GC in a lot faster manner. In the conclusion, if we have a discrepancy between kappa density and AGA-8 density, this can mean, first, we got issue with the temperature. So we can then perform a spot check to see if there is issue with the temperature. There might be issue with the pressure letdown system. We can then perform a spot sample test and see whether the composition as a result of the spot sample is similar to the composition that is being read by the GC. issue with the GC. This can be confirmed by looking at the parameters on the GC CBM. There might also be issue with the USM. We can then utilize the USM CBM method to confirm the health of the USM system. Now, the only thing that we really need to pay attention on this here is that no discrepancy between the kappa density and aga-8 density does not mean that everything is okay. It can still mean that there might be issue with the pressure, because in this, as you can see from this case here, we don't see any discrepancy on kappa density and aga-8 density, even though there is issue with the pressure. The other thing that is a conclusion here is that low life uncertainty does not mean that the system is healthy. Life uncertainty only tells us half of the story. Life uncertainty is only valid as long as all the instrument is working correctly in a healthy manner. If some of the instruments not working correctly, we will see, or we can still see, low life uncertainty is just giving us error in the system. I think what we should do is to have a combination between life uncertainty check and a cross validation method, and that can provide a very meaningful insight on the system health. Here's some ideas for the use of the cross validation method that we have. What we can do is, first, we need to optimize the GC to ensure that the GC works correctly. We then use all the available methods to ensure the USM measures correctly. This comes from the calibration of the USM as well as footprinting method. From there, we can take the initial good data comparison between the GC and USM. What we then do, set this as a footprint. Once this footprint is set, then we can compare data between the footprint and the real data of the USM. We can then set a alarm limit based on the actual capability of the GC USM. As an example, instead of using 0.2% as a tolerance for speed of sound, based on the capability of the GC, where it's normally sits at 0.016%, maybe we can set the tolerance at 0.3%, 0.03 or 0.04%, and therefore it's a lot more representative to the actual capability of the USM and the GC itself. We can then do checks when alarm occurs. So this is instead of performing preventive maintenance. Also, we need to make sure that there are means to check the pressure transmitter accuracy, because the pressure transmitter is the dark horse here. Is basically, if we have issue with the pressure transmitter, this method will not be able to identify that issue. Just to acknowledge as well, this particular data looking at this issue has also been written before on papers earlier, so this is nothing new that I've done here. Patrick Arnold have wrote an amazing paper in 2021 talking about the sensitivity of these parameters towards the output. Okay, so just looking at the other potential of the SMA itself, first we can actually perform a virtual flow metering, where we can perform live data validation and reconciliation. That means we can actually take the input that goes into the flow computer and also perform the SMA on calculation, and then therefore we can actually then perform a live data validation against the calculation that is performed by the flow computer. We can also do mismeasurement. So in case of mismeasurement is identified, we can take that same data and implement the new data in there, and therefore we can then do a calculation based on the new input, and then therefore we can do the mismeasurement that way. We can perform live uncertainty as shown before. We can perform live mass balances and any other type of cross-validation. For example, the calculated density versus densitometer in the system that has densitometer. For example, on the orifice system, it might be very, very useful to have a densitometer in there, and therefore we can perform a cross validation between the calculated density and the measured density. We can optimize the measurement system, making sure that all the meters are working correctly. We can monitor the performance of the measurement system, and then basically, if you can do the math, anything can be implemented. So pretty much anything that we know of the input, and then we can actually do the math to give an output based on this input, can create the DLL functions for it, and then we can represent it in the SMA. So that's my presentation on the cross-diagnostic validation between USM and GC. If you got any question or you want some extra information with regards to SMA or the method is presented here, please don't hesitate to get in touch. Thank you.